Okay, solid angle of practical antenna. Okay, next parabolic reflector. Okay, next parabolic reflector. Okay, you know that parabolic reflector we are using in DTH receiver. Okay, where parabolic reflector is used in DTH home, direct to home receiver, DTH receiver. Okay, we are using parabolic reflector. Then what should be the gain of the director? Okay, what should be the gain, and what should be the other parameters? Okay, so again, say this is the parabolic radiator. Okay, it is having some shape here like this, and again you might have seen there will be one feed like structure here. Okay, one feed will be here. What is the job of that feed? Again, you might have seen that feed will be connected to some wire, again that will be taken to your set-top box receiver. Okay, see, set-top box receiver, set-top box receiver. Okay, so what is happening? Directly signal is not going to the feed, but actually signal is falling like this. Okay, signal will be coming like this, will come like this. But the shape is in such a way the reflected signal will go here. Any reflected signal will go to this feed. So that is the idea of the parabolic reflector. Instead of simply receiving the direct signal, once if you receive like that, you will get receive very less signal. That signal strength is not enough because signal is coming from the satellite very long distance. So to increase the signal strength, to increase the signal power, we are using the feed. So we are using the reflector, parabolic reflector. So whatever the signal that is touching on, that is incidenting on this parabolic reflector is reflected back in such a way that they are all focused on this point. They are all focused on this point. Again, you know mathematics. So once if you have kept your feed exactly at the focal point of the parabola, then all the waves that is falling on the parabolic reflector will be definitely collected by this feed. Okay, once if you are not keeping your position properly, then you will not receive proper signal. Okay, so then with the cable, then you can take that signal to the set-top box receiver. Then later you can see the TV program. So now what is this? What is the directivity of this parabolic reflector? That is very, very important. What is the directivity? What will happen if the directivity is missing? Okay, so the directivity of the parabolic reflector is very, very, very high, very, very narrow, because if you have seen what is the directivity like this, see, it's like around 1 degree, the directivity of the satellite and all radiating the energy in 1 degree angle, because even if it radiates at 1 degree angle, solid angle, that can cover almost 1/3 of the Earth's surface, because it is at much larger distance. That's why the directivity is very, very high. Even if you tilt your antenna by a 1 centimeter above or below or in the side, definitely you will not get signal, because there has to be a line of sight between the satellite and the parabolic reflector. Okay, so once if you are not maintaining the line of sight, that means what? You are not maintaining the directivity. Okay, the beam is very, very, very narrow. The beam is very, very narrow. So the directivity of the parabolic reflector is very, very high, because it is long distance communication. So whenever you have long distance communication, the directivity is very, very high. That's why even if you tilt your antenna by small amount, you will not get signal. But the same problem you will not experience in the mobile phone, because even if you tilt your mobile phone, you are getting the signal. Their directivity is different. Their directivity of your mobile tower and your mobile antenna is different. Here the directivity is completely different. Okay, so because whenever you are doing long distance communication, directivity is very, very high. Please note down that point. So long distance communication. So whenever you have long distance communication, directivity is very, very high. Directivity is very high. You know, once if directivity is very high, definitely beam width is low. Definitely beam width is low. Beam width is low. A very narrow beam width. So this radiation pattern and all will be having the very narrow beam width. So then what is the directivity of the parabolic reflector? So before that, you should know the diameter of the dish. Okay, diameter of the dish, that I call it as D. Okay, diameter. Don't get confused with the diameter and directivity. For both, we'll use same notation. Diameter of dish. Okay, in meter. Okay, in meter. Then once if you know the operating frequency. Once if you know the operating frequency, then you can calculate the wavelength. Once if you know these two, then you can directly calculate the directivity. So directivity is equal to 10. Other, please mute the mic. 10 d by lambda whole square, very important. So the directivity of the parabolic reflector is 10 d by lambda whole square. This d denotes the directivity. This d denotes the directivity. Directivity is means it is just a number, no unit. See, d square divided by lambda square. Unit of d is meter. Unit of wavelength is also what? Meter. Both will cancel. Finally, you will get no unit. Okay, so 10 d by lambda whole square. Simple formula. Okay, simple formula. This d indicates the diameter. Okay, this d is diameter, this d is directivity. Okay, so now you I will give you some example. You know what is the frequency of operation for DTH? Okay, then what is the frequency of operation for other satellite communication? Okay, other satellite communication frequency of DTH. Anybody? What is the frequency of DTH?
4 to 6 gigahertz, sir.
அப்படியே மார்க் சொல்றீங்க. 12 to 14 gigahertz. Okay, the directivity of the frequency of DTH is 12 to 14 gigahertz. Okay, for other satellite communication we are using 4 to 6 gigahertz. Okay, you take some middle frequency, some frequency. Once if you take some frequency, you'll get some wavelength. Okay, then you know the approximate diameter of the dish. It is roughly around, I think, 1 meter or 120 centimeter, like that. Okay, DTH. And you know what is the for other satellite communication, the diameter could be around 5 meters, something like that. Okay, so then you know the values, you just substitute here in this formula. Then what is the directivity that you are getting? What is your directivity? Okay, கண்டுபிடிக்க முடியுமா? Yes, diameter கொடுத்துட்டான் approximate. Frequency also, you know, you take any one of the frequency, you calculate lambda, then finally you will get directivity in terms of number. For that you can take dB also. Okay, once if you have number, okay, then for that you can take dB also. Okay, so once if you take dB directivity, if you want to represent in dB, 20 lakh use pannuma, 10 lakh use pannuma, sir? Anybody? I know this value. 10 lakh. What about others? See, somehow I have calculated all this value. I know D. From this D, how can I represent in dB? Directivity in dB. 10 lakh, 20 lakh. Anybody? Directivity means 10, it is giving you the power gain or voltage gain. 10 lakh. Yeah, 10 lakh. So 10 lakh D, simply D. This D means this D, directivity. Okay, not to make confusion, I'll make the colors like this. Okay, this D means this D. Yeah, somehow I have calculated D. Once if I know the D, because D I have calculated in the power domain. Okay, gain means power gain. Okay, power gain. So 10 lakh D. Okay, now just you calculate the directivity in terms of number as well as in terms of log. That's okay. Then you also calculate the directivity for other antenna if possible. Now I will give you the directivity of lambda by 2 dipole and monopole antenna and other antenna. Then you compare the directivity of this antenna with the dish antenna. Okay, how the directivity differs. Okay, so now next one is, you know, directivity, then what is the gain of the parabolic dish? Okay, gain of the parabolic dish. So very simply, gain of the parabolic dish is equal to, instead of 10, you put 6 here, 6 d by lambda whole square, 6 d by lambda whole square. That means what? Gain is equal to efficiency into directivity. Here in case of parabolic reflector, the efficiency is 0.6 or 60%. That means what? Out of all area, around 60% of the area is effectively collecting the power. Remaining area is not collecting the power. Okay, see what is the meaning of this one? Only 60% of the area, 60% of physical area physical area is effectively collecting the power, collecting the power. So without worrying about anything, simply you remember the formula. Okay, directivity means 10 d by lambda whole square. Okay, then gain means 6. Okay, that's a way. Next, what is the beam width? What is the beam width? Somehow I told you, once if you have a dish like this, okay, if this is my dish, okay, then how will be the directivity? Okay, definitely, suppose if it is a transmitting antenna, it can be a transmitting antenna, receiving antenna, no problem. Okay, so the dish may act as either transmitting or receiving, that's okay. So again, see, the directivity will be something like this, because the power is flowing only in this direction, the satellite is upwards. Okay, so now what happens, the directivity is going in this way. So once if you tilt somewhere, the satellite position will be here. Suppose if satellite is there, okay, now the directivity is like this. Okay, this beam is of very, very narrow. So once if you tilt by even by 1 centimeter upward or downward, you will go somewhere else. Your beam goes somewhere else. Okay, this is true for both the transmitting as well as for the receiving antenna. Whenever you are receiving, your beam will be coming like this. Then if your position is like this, then only you can receive the signal. Okay, if you tilt your antenna by some other means, in some other way, then you will not receive the signal. So the beam width is very, very narrow. Okay, because of long distance communication. Now what is this beam width? Okay, what is this beam width? Okay, beam width, what is the beam width? Okay, the beam width formula directly I'm writing. So beam width, okay, it's very important. In the question அடிக்கடி எக்ஸாம்ல வந்திருக்கு. Beam width is equal to 140 degree divided by d by lambda. Please always remember in some format. ஒவ்வொரு புக்ல ஒரு ஃபார்மேட்ல கொடுத்திருப்பாங்க. Always remember in some format. Beam is equal to 140 degree divided by d by lambda. So இதுக்கு பின்னாடில some derivation is there. Okay, don't worry about the derivation. Simply remember the formulas. Exam point of view. 140 degree divided by d by lambda. Where what is d? D na directivity or diameter, sir? Anybody? Beam with 140 degree divided by d by lambda தராங்க. இங்க இருக்கிற d வந்து directivity.
Diameter.
Yeah, diameter, because as per the unit concept, length by length has to cancel. Beam width is in terms of degree. Beam width is in terms of degree. Yeah, or some book they used to give like this 140 degree lambda they'll take up. They'll also give like this. Okay, no problem. Everything is okay. Now, and again, one more ratio is there. F by d ratio, focal length to diameter ratio, or simply they'll call it as F by d ratio. Very rarely they used to ask this question. What is F by D ratio? Okay, F by D ratio. F by D means what? Where is your focal point? Okay, sorry, where is your focal point? Okay, where is your focal point? Then what is the diameter of the disk? What is the diameter of the disk? What is that ratio? That ratio is given by F by D. F by D ratio, F by D is equal to, simply remember, 0.25 cot theta. So in the question they will give you only theta, sir. They will give you only theta. They will ask you F by D. So you have to remember this formula, 0.25 cot theta. Okay, F by D ratio. Then in parabolic reflector, generally there are 3 types of feeds. Okay, 3 types of feeds, and each feed is having its own advantage and disadvantage. The first one is front feed. Okay, front feed means what? Where you are placing this signal collector. This is called as feed. Even for signal collection or for transmission, whenever you are transmitting, this will give the radiation to the disk. Okay, that will again reflect to the space. That's idea. That's the idea. Okay, for transmission or reception, both are okay, same. Okay, so what is the feed here? Okay, front feed. So what is the problem when you have front feed? Okay, I will draw it in 2D. Suppose my disk is like this. Okay, now I am in a transmitting mode. Say for example, I want to transmit the signal. My dish has to act as a transmitter. Then what I will do, my feed is here. Okay, I am connecting my transmitter to this feed. Then this will give the electromagnetic waves. Okay, this will give the electromagnetic waves. This goes like this, like this, like this, like this. then what is happening, it is going like this, then later it will go in this manner. Okay, in this manner. Okay, so in this process, what is happening? Some signal is here. Here is the problem. So again, if the signal gets reflects here, then it is stopped by this source. Okay, feeder. Okay, so that means what? Some part of the signal is stopped by the feeder, and again, your feeder job is only to give the signal, but now here it has to accept the signal. So what will happen? The stability of the feeder will be affected. The stability of the feeder will be affected because its job is to give the electromagnetic signal to the disk, but in this process, as it is exactly getting reflected here, and again it has to accept the electromagnetic energy, then again the stability of the feeder is lost. Okay, that's one major problem here in the front feed. Okay, so whenever you have a front feed, then this is the problem. Okay, stability of the feeder is affected, okay, due to the reflection. Okay, so stability of feeder affected due to reflection, and one more thing I want to point out here, this is not related with that is front or, okay, I will discuss about this later. Now I will do the classification alone first. Next feed is Cassegrain feed. Okay, next feed is Cassegrain feed. Okay, so Cassegrain feed. Okay, here what is happening? So here, instead of one reflector, they are using two reflector. Okay, this is main reflector and one sub reflector. Now to overcome the stability problem, okay, they are placing their source here, feeder here. This feeder is giving the signal to this, okay, to this. Then it goes here, it goes here, it goes like this. Now this stability problem is somehow we overcome, but what happened? Okay, here we are using two reflector, main, primary and sub reflector. Okay, this is primary reflector. This is sub reflector. Okay, now what is happening here? Stability somehow you have overcome. Your source is not affected by anything because you are giving the signal in such a way it is not getting exactly reflected. It's going away from this, then it's going here. But what is happening? This portion is not sending any signal. This sub reflector is stopping some amount of some amount of electromagnetic waves. Okay, so and again you are losing your electromagnetic energy. Okay, see what is happening in this portion, you are not getting any signal. Okay, see the EM waves is stopped at the direction of sub reflector. Okay, no EM waves. Waves stopped by sub reflector. Okay, then to overcome this issue, we have offset feed. Okay, we have a offset feed. Okay, in case of offset feed, if your dish is here and your feeder will be here, okay, this is your feeder, then the signal goes like this, okay, then it goes like this. Here, what is the problem? There is no stoppage, but only some portion of the parabolic reflector is illuminated by the EM waves. Okay, see, and again, here, what is the advantage here? First we see the advantage. Advantage here is no aperture blockage, and again no impedance mismatch. No aperture blockage, no impedance mismatch. Okay, this is most important. Mostly they'll ask in the exam, what is the advantage of offset feed? That is no aperture blockage. Okay, no impedance mismatch. Then what is the limitation of this method? Here also only some portion of the primary reflector is illuminated. Only some portion of reflector is illuminated by EM waves. Reflector is eliminated by EM waves. Okay, EM waves. So next they'll ask one more question. The main concept of the parabolic reflector is, say for example, if you have a parabolic reflector like this, okay, like this, you are having a source here. When you are having a source, you know, when you have a source like a point source, that will create a wave in a spherical shape. Okay, spherical waves. The waves created by this point source is called spherical waves. Okay, you know that whenever you have a point source, that will produce a spherical waves. Okay, then in the process of reflection, what is happening in the process of reflection? What is happening after the reflection from this parabolic reflector? Your wave goes like this. Okay, your wave goes like this. So what is happening? This wave is called spherical waves. This wave is called spherical waves. This wave is called plane waves. Okay, one day I will do the simulation or who will be the plane waves. This is the example for plane waves. Okay, see, this is the example for plane waves. Okay, this is the example for spherical waves. Okay, so again, your parabolic reflector is converting the spherical waves into the plane waves. Another important concept in the exam they will ask. Okay, what the parabolic reflector is doing, it converts the spherical waves, okay, spherical waves into the plane waves. Okay, so very important. Parabolic reflector, okay, parabolic reflector converts spherical wavefront, spherical wavefront into plane wavefront, plane waves. Then what is the advantage of this one? Okay, it is converting spherical waves into plane waves. Whenever you have a spherical nature, your power diminishes very quickly. When your wave is having the spherical nature, that means what, it goes in all directions spherically. When it spreads spherically, that power of the wave diminishes very quickly. But if it is in a plane format, the power will not diminish quickly. That is the main idea. That's why this plane wave goes to longer distance. Okay, see, if it is in a spherical format, the power of the wave will diminish very quickly. But as it is converted into the plane waves, the plane wave can go to the longer distance without much loss. That's another idea. That's why the directivity of the parabolic reflector is very high. See, please make one note. Whenever wave is of in a spherical nature, the decreases power of the wave decreases very quickly. When wave is having spherical nature, spherical nature means spherically it spreads the power. Spherical nature, spherically in all directions, spherical nature, the power of the wave decreases very quickly. The power of wave decreases very quickly. Because that's okay, because whenever wave is going in all direction, definitely the power will reduce. Because if it goes in only one direction, the power will not reduce. Simply you think it of, say for example, when you are calling some person, when they are near, okay, you'll simply call them. But when they are far away, what you are doing, traditionally you'll keep your hand near to your mouth, then you focus your energy in a particular direction. Okay, that means what, somehow you are converting the spherical waves into plane waves. Okay, you are aiming to concentrate the sound energy in a particular direction. It's something similar to that. Okay, if the energy goes in all directions, then the power will reduce very quickly. If it goes only in one direction, the power will not reduce.